So we're continuing our journey of looking at the equation and trying to give us certain determine information about what the graph of this function is going to look like. Okay, so we're now looking at the first derivative test. We just finished talking about whether whether or not we have a maximum or a minimum, an absolute max, an absolute min, a local max, local min. So a lot of things going on there, but really what was important from that last section was our ability to find critical points. Okay, so there's going to be some things in this PowerPoint that I'm probably not going to focus on as much as the PowerPoint does, but I do want it here as a reference for you because you may read this and find out something different or see something different than what I'm able to tell you. So let's look at a couple of these first, okay? There's some things about the mean value theorem which we've not talked about yet. So we're going to talk about the mean value theorem later. But in essence, what we really wanted to talk about was, let me get my pen handy right here. What we really wanted to talk about was the fact that we have these intervals of increasing and decreasing, okay? So we're going to use the idea that the derivative of a function is positive, then the function is increasing. If the derivative of the function is negative, the function is decreasing. Okay, so that's really the focus of this first derivative test. And here, I like to approach things from a graphical standpoint. So I think that you can see in this first graph here, the y, as we read from left to right, the y values get bigger and bigger and bigger. Okay, so that's really where I want to focus on. I think we can all agree that this function is increasing. Okay, but what I want to focus on are these dashed lines, right? These tangent lines. Notice how the slope of these lines is positive. And because the slope of the tangent line, right, the derivative is greater than zero, that's just a fancy way of saying positive, we say that the function is increasing on this interval. Notice what happens here. These y values, they're still increasing, right? They're still increasing. I can tell that because the slope of those tangent lines are positive. So both of these, A and B, show functions that are increasing. The curvature is what's different, okay? We'll talk about the curvature in another video. Down here on the bottom, you can see now I have tangent lines that are negatively sloped. In other words, the derivative is less than zero. The derivative is negative. So we have a function that's decreasing on this interval. Again, these tangent lines are negatively sloped. And so all that's really changing is the curvature of this. And again, we talk about the curvature in a subsequent video. So here's some information that you might want to take the time to read. A continuous function has a local max if and only if f switches from increasing to decreasing. So what I want you to notice is if we have a function that was increasing and now that function is decreasing, we say that this value right here, this x value c, is a local max, okay, because we were increasing, right, and now we are decreasing. So this would be this would be a place where we have a local max. If f has a local min, right, that means that the function switches from decreasing to increasing, okay? And those are fancy ways of saying if the derivative is negative, right, less than zero, that function's decreasing. So what we want to be able to do is kind of look at the information that our derivatives are giving us and make some inferences on what our function is going to look like. The only way that f prime can change signs as x increases is if the derivative at c is equal to zero. Okay, so that's that critical point that we found. So we're going to do a couple of problems where we talk about exactly how to do this. Okay, so here's something that I wanted to make sure we discuss in detail. You'll notice that A right here, A is a critical point. Okay, critical point. A is a critical point because the value of the derivative right here is undefined. Remember, this is a point of non-differentiability. And we said a critical point happens when we have a derivative that's 0 or undefined. Okay? Now here's what I want to point out to you. If you look at the tangent lines, here the tangent lines have positive slope, right? Because as we go from left to right, it's positive slope. Here, those tangent lines have a negative slope. And so we would identify that as a local max. Again, we changed from increasing to decreasing, okay? And you'll notice right here at B, this is another critical point, right? It's a critical point because again, the value of the derivative right there is 0. But what I want you to notice is that the tangent lines go from decreasing, right? That's a negatively sloped line, to positively sloped, okay? So we would say that this is a local min. Now, right here, you'll notice the slope of the tangent line is positive, and then here it's positive. So there is no change, right? There's no change in whether or not the tangent lines are positive or negative. In other words, the derivative is greater than 0 on both sides of C. But you'll notice that C is a place where the derivative is 0. So this is what's called a saddle point. Okay, and I'm not sure that your homework addresses saddle points, but just know that it's there. And if your derivative does not change sign, we can't say that there's a max or a min. So this is neither a max nor a min. And then right up here, we have one more place where we have a maximum. We went from increasing to decreasing. Okay, so that is a max. So I used to take my classes to Six Flags and we would ride the rides. So if you're not familiar with what Six Flags is, it's one of the theme parks, Busch Gardens, all the others. And we would get on the roller coasters where we'd go down the big hill and then we go up and then we go down again. And so the point of it was just so that they could experience, physics and all those things that we study about but never really get to experience. And when we were a bunch of nerds, and when we got to the top of the hill, we would holler local max, and we got to the bottom, local min. So it's just some fun ways to try to bring some of this stuff home. Okay, so let me go back here. Take a look at the function y equals x to the 7th. Is the inflection point x equals 0 a local max or min? Okay, so in other words, what we want to know when we say is this point a max or a min, a local max or min, we want to know, does the derivative change signs at x equal negative, at x equals 0? Okay, so does the derivative change signs at x equals 0? If you go back to that previous graph, you'll notice, look, right in here, we used these x values to say that the derivative was greater than 0. What do you mean we use those x values? So I looked at this point and I said the slope of the tangent line at that point is positive. Okay, so we're looking at values on either side of 0. If you drew a number line and 0 were here, -1 would be here and 1 would be there. And so we plug -1 into the derivative of this thing, 7x to the 6th, and we get a positive 7. We do the same thing with +1, we get a positive 7. So because the derivative does not change signs, right? This thing is not a local max and it's not a local min. So we're asking a similar question. We're asking about increasing, decreasing, right? In this case, we're asking about the intervals over which the function is decreasing. But what I want you to notice is this thing right here. We're not looking at the function, we're looking at the derivative of the function. Okay, so right here, we're looking at f prime. So we said that when f prime of x, there it goes, when f prime of x is less than 0, this thing is decreasing. Well, it's less than 0 on these parts, here and here. In other words, it's decreasing on the intervals from -infinity to -2 and from -1 to +2. Now I know you would look at this and you would say, but as you go from left to right, you might say the y values are getting bigger and bigger, right? Wouldn't you say the y values are getting bigger and bigger? But notice what we're looking at. We're looking at the graph of the derivative, right? And so negative values are all of those values that occur below the x-axis, okay? So that's why we would say that it's decreasing on this interval. So the first derivative test is really what we're using when we look at these problems. We're testing the value of the first derivative, and that's what we did here. We said the first derivative is positive 7, and down here the first derivative is positive 7. Because there was no change, we said that there's not a maximum and there's not a minimum, right? So look at what the first derivative test says. If the first derivative of f prime changes from positive to negative, right? The derivative changes from positive, in other words, from positive to negative. This is positive, this is negative. We have a local max, right? There's our local max. If the derivative changes from negative to positive, right? Negatively sloped tangent lines all the way down here, all the way down here to positively sloped tangent lines. Okay, so this is a situation where we have a local min. But what's more important is that f prime on this side is less than 0 and f prime on this side is greater than 0. If f prime has the same sign, right, in other words, it doesn't change, then there's neither a local max nor a local min. Here's an interesting question. Again, we're looking at the graph of f prime, okay? This is a graph of the derivative. What is the greatest value for x at which there is a local minimum? Now remember, for local minimums, we want f prime to go from negative to positive, okay? Where does f prime go from negative to positive? Well, at -1, this goes from positive to negative, so we're going to throw that out. At 0, it goes from negative to positive. We want to think about that one, right? Here we go from positive to negative, we throw that out. So it turns out x equals 0 is the biggest x value and the only x value where we have a local min. If you forgot, remember local mins are indicated where we have a change from negative to positive. Here's another problem very similar to what we just did, but what I wanted to get to was a problem like this, okay? It says determine the critical points of f and locate all local extrema, okay? Locate all local extrema. So what we're going to do in this first problem here is we're going to find f prime of x. The second thing we're going to do is set f prime of x, set f prime of x equal to 0 and solve. So I'm just going to put and solve, okay? In other words, take the derivative, set it equal to 0, okay? In order to locate the extrema, right? So from step 2, right, from step 2, we're getting those critical points, okay? But in